Good morning, everyone. I am Usman K, Assistant Professor, VITM, Ballari. First, I welcome you all to my sixth video lecture on Model 4. So, in the previous video lecture, we discussed about various types of perspective projections, and we also discussed how to perform normalization. So, these are the two concepts I discussed in the previous class, and we also seen what is the shape of the viewing volume either in case of perspective projection or in case of parallel projection. In case of parallel projection, the shape of the viewing volume is like a one rectangular shape of parallelepiped structure. In case of perspective projection, the shape of the viewing volume, it is like a frustum or it is like a pyramid. So the shape and structure of the viewing volume, it depends on type of the projections we selected here to project a given object on the projection plane. So today I would like to continue that topic only. That topic only. So uh, now I completed all the types of projections. Means I discussed what are the types of parallel projections and what are the types of perspective projections. And I also said how we can translate position of the object or uh, position description of the every object on the projection plane using projections. Now I want to continue perspective projections topic. Now, in case of parallel projections, we discussed what are the parallel projection coordinates. Similarly, when we are using perspective projections, then we should know what are the perspective projection transformation coordinates. So let us consider one example to demonstrate perspective projection coordinates. So assume that there are two line segments are there, and I can say that see the example, see the figure or see the image. Assume that there are line segments are there, two line segments are there, and we have a one projection plane, or I can say that we have one view plane here, and we have a converging point here that is called projection reference point. So please you consider three things in this particular image. First two line segments are there. Those line segments are called objects. Next, we kept projection plane between the object and projection reference point. Means here our camera is located at the projection reference point. Between the projection reference point and object, we kept projection plane. Now, what we need to do means here we need to derive equation for the perspective projections. So to perform the derivation, we should know that what is the outcome of perspective projections when I translated object coordinate position from the space to the view plane. Now you see that here. Now you see that we kept two equal length line segments at the different distances from the view plane. Means the size of the objects are same, but we kept those two objects, that is line segment, at the different distances from the view plane, but the size of the line segments are equal. When we are viewing this two line segment from this particular point, see the mouse pointer, from this particular point, then when we are using perspective projection, we know that whichever the object that is closer to the camera, it looks larger in size, and whichever the object that is far from the camera, the size of that object will decreases or it looks very smaller. This is the property of the perspective projections. So we should derive that. To derive that, see that here. Please you see that here. We are viewing a two line segment of equal size with different distances from the camera position to object, or in other words, there is a difference distances between projection plane to line segment. So assume that please you see that this is the first line segment and this is the line segment, second line segment. Assume that distance between first line segment to view plane is 1 meter. Next, assume that the distance between second line to view plane is 50 meter. I will repeat. The distances between first line segment, this is a first line segment, and view plane is 1 meter or 1 kilometer. The distance between second line segment to the view plane is assumed that 50 kilometer. Now, when we want to project this line segment image on the projection plane, whichever the line segment closer to the projection plane, it looks larger. So as you can see this example, when you are capturing the two images, first line segment and second line segment using real camera or synthetic camera, after capturing or after transferring position of the coordinate position of the line segment on the projection plane, as you see the projected image on this on the view plane. So both the line segment coordinate positions are translated to the projection plane. But see the sizes, see the size. So first line segment, the distance is only 1 kilometer from the projection plane. Hence, that object looks larger. So the same line segment I drawn on the projection plane, it looks larger size. So I drawn larger size line segment. Same line segment, it is second line segment, but it is 50 kilometer from far from the projection plane. Then it looks very smaller. So as you can see that I projected second line segment on the projection plane by using perspective projection. The size of the projected line segment on the projection plane is very smaller. So this is the property of perspective projection. So I written very clear sentence here. See the mouse pointer. A perspective projection of two equal length line segment at different distances from the view plane produces or creates or projects a two different images on the projection plane with two different sizes. Means size of the object projected on the projection plane, it is directly proportional to the distances. Smaller distances object looks larger, longer distances object on the camera film looks very smaller. So today we need to derive this particular concept. Now, before deriving perspective projection coordinate transformations, first we should know three things. Means we need to determine three things with respect to this particular topic. First, we need to determine projection of a line segment on a view plane. So as you can see this diagram, this is nothing but projection of a line segment on a view plane. So whatever the line segment I projected here, this is called projection of a line segment on a view plane. So we need to determine, this is the first thing. When you want to determine projection of a line segment on the view plane or projection of an object on the view plane, we also need to determine position of the projection plane. Means here I kept projection plane between the object and projection reference point. You can place projection plane in three different places, as we already discussed in the previous video lecture. You can place projection plane in a positive z axis place, or you can place projection plane parallel to the our xy plane, or you can place the projection plane in the place of negative z axis. Means these are the three positions are there to place the projection plane. So we need to determine that position also with respect to projection plane. Third, we need to determine position of the projection reference point. So here, as you can see that this is the position of the projection reference point. So we need to determine where I can place the projection reference point. This is nothing but position of the camera, or position reference point it is, right? So these are the three things we need to determine with respect to this particular topic. I will repeat: determine object projection on the view plane, or you need to determine projected object position on the view plane. Second, you need to define what is the position of the projection plane. Third, you need to define position of the projection reference point. So these are the three things we need to determine with respect to this particular topic. But we know that every line segment contains two endpoints. So instead of determining projection of line segment on the projection plane, we want to derive projection coordinates with respect to perspective coordinates, or we need to determine what is the perspective projection coordinates with respect to only one point. So instead of calculating or instead of determining projection of the line segment on the projection plane, we are determining only projection of a one point P on the view plane. So if you understood this same concept, we can apply to determine what is the projection of another point of the line segment on the view plane. But we are deriving only for the one point. I written clearly within the bracket. Instead of determining projection of a line segment on the projection plane, here we are considering only one point. So I can say that first point here, as you can see that here, this is the first point. So for first point I am taking as a point P. So now my aim is, I would like to determine what is the projection of a point P on the view plane or on the projection plane. Let us consider there is a one point in the space. This point represent one object is present in the space. For this point or for this object, we need to determine its corresponding projection coordinate on the projection plane. That is called P dash. So P is the one point of coordinate xyz present in the space. When you translate this point P on the projection plane, its coordinate will become P dash, where P dash is XP, YP, Z, BP. So this is nothing but our perspective projection coordinate with respect to point P, that is called P dash. And we have a projection reference point here, means we are observing this object in this direction. So we have a perspective projection point here. So here we have projection reference point P. This is nothing but assume that R it is R R. Okay, capital R is there. This is called projection reference point, and its three coordinates are XPRP, YPRP, ZPRP. So this is the one point, means it is the origin of the camera, you can think that, right? This is the projection reference point, and this projection reference point is also having its own coordinates like x view, x view, y view, z view. This is nothing but viewing coordinates, or assume that we kept the camera here, or I can say that camera coordinates here, right? So we decided here three things. One, object is located in the space and its position is P of XYZ. When I translated or when I projected this object position on the projection plane, then its coordinate will become P dash, and its coordinates are XP, YP, ZBP. And we defined origin of the camera, that is called R, and its position is X projection reference point, Y projection reference point, Z projection reference point. And now you can see that I drawn one dashed line. This dashed line represent, it is a projection lines like our rays. In case of real camera, when you capture the image or when you capture the object from the real camera, that captured image is reflected, it is displayed on the camera film with the help of reflected rays only in the real camera. Same logic we are applying in synthetic camera. Those rays is nothing but here, this is called projection lines. Now when this projection lines, when this projection lines passing through the projection plane, and when it is intersecting to the point P, then that intersection point generates or creates one point P dash on the projection plane. That P dash is called projected point P on the projection plane. So like this, we are translating position of the object in a three-dimensional space into two-dimensional viewing plane. So we need to consider one point here. Now, this is the one derivation is there, but I would like to derive this in the next class, in the next video lecture. Now I am explaining only this, how, what are the concepts we need to determine with respect to perspective projection coordinates. So first we need to determine projection of a point P on the projection plane. This is the first point we need to determine. Second, we need to define position of the projection plane. So you can place the projection plane in different places. As I highlighted in the first point, projection plane can be placed between the projection reference point and object. So as you can see this diagram, we placed projection plane between the object P and projection reference point. This is a one position of the projection plane. Like this, there are various positions are there. You can place the projection plane. So first point I said here, you can place the projection plane between the projection reference point and object. The example is this only. What we did, we kept view plane between the object and projection reference point. This is the one position. Second position is, if the projection reference point is between the object and projection plane, then objects are inverted on a view plane. Means when you place projection reference point between the object, this is nothing but our object. Line segment is there. I drawn one arrow here. This is nothing but one line segment is there in the space. This is nothing but one object. Now what I did, I kept object here, but I'm not discussing about the object here. I'm discussing the position of the view plane. If I place view plane, or if the projection reference point, if the projection reference point is between the object and projection plane, then we will get the inverted object image on the view plane. So as you can see that I kept object here, that is called one line segment, and we have a projection reference point here. If projection reference point is between the object and view plane, then definitely we'll get inverted object image on the view plane. As you can see that arrow is in the upward direction. This is one line segment that is there in the space. When I capture this image by using synthetic camera in a such a way that if I place the projection reference point between the object and view plane, then the inverted image I will get on the projection plane. So this is the second position here. In the first example, I kept projection plane between the projection reference point and object. Now I kept projection plane at the end. At the end means first we have an object, see the mouse pointer. Next we have a projection reference point. Next I kept the projection plane. This is the second possibility of placing view plane and getting the inverted image. Third is, if you place the object in between the projection plane and projection reference point, then object may be enlarged. What I'm saying here, when you place the object between the projection plane and projection reference point, the size of the object will get larger. This is the property of perspective projection. So here these three example represents we are placing projection plane in three different places. First, we kept projection plane between object and projection reference point. In the second example, we placed projection plane at the end. At the end means first we have an object, next we have a projection reference point. Third, we placed view plane. In the third example, we are placing object between the projection plane and projection reference point. Then the size of the object will get larger, or I can able to see that image size is larger. This is the three different places where I can place the projection plane in our synthetic camera. Next is position of the projection reference point. So please I will repeat with respect to this slide. First we discussed how to get projection of a point on the projection plane. So derivation I did not derive, but derivation is there for this particular topic. I would like to derive the derivation of this particular point in the next video lecture. Second, we define position of the projection plane in our synthetic camera. Third, we need to determine position of the projection reference point in our synthetic camera. So the output of the perspective projection depends on the distance between projection reference point and view plane. What I am telling is the image or coordinate position of the object what we translated on the view plane, it mainly depends on the distance between the projection reference point and view plane. So how it differs, we will see the various cases. Means please remember, whatever the image you projected on the projection plane, it depends on the distance between the object and camera in real camera. But in synthetic camera, the size of the object that is displayed on the projection plane, it mainly depends on the distance between the projection reference point and view plane. Projection reference point means assume that it is our camera or our eyes located at that particular position. Or projection reference point is nothing but origin of the camera. Means from the origin of the camera and view plane, whatever the distance is there, based on that distance, we will get the various size of the image on the projection plane. So let us see the various cases. Case 1 says that if projection reference point is closer to the view plane, means if you place the camera near to the view plane, then closer objects will appear much larger than the more distant objects of the same size. What I am saying here means, when you place two different objects of same size, same shape, but distance is different from the projection reference point and view plane, then whichever the object or whichever the line segment that is closer to the projection reference point, or whichever the line segment or whichever the object that is closer to the our camera, the size of the object will become looks larger. As you can see that, as you can see that in this example, we need to assume we kept projection reference point here and our clipping window is here, and you assume that our clipping window is nothing but here we have a view plane. So we assume that we kept view plane near or closer to the projection reference point. If you place view plane closer to the projection reference point, object size looks larger on the view plane. This is the first case with respect to view plane is placed near to the projection reference point. This is the one position. Second position, you see that second position of the projection reference point is we kept projection reference point far away from the view plane. Means we place projection reference point at this certain distance compared to the case one. It is far away from the uh, projection reference point compared to the previous example. So assume that in the case one, we kept projection plane at the distance 1 kilometer from the 1 meter. Sorry, 1 meter. Assume that in case one, we kept projection plane. Clipping window is nothing but projection plane only. Assume that in case one, projection plane we kept at the distance 1 meter from the projection reference point. So object looks larger in case one. In case two, assume that I kept projection plane at the distance 2 meter from the projection reference point. So 2 meter means I kept projection plane far away from the view plane. Then the difference in the size of near and far object decreases. Means what I am telling means, when you place projection plane or view plane far away from the projection reference point, large A object that is nearest to the view plane looks larger. If any object that is far from the projection plane, that looks very smaller. So this is the property of the our eye also. So when I place the object near to our camera, the size of the object will looks larger. Same object I will place far away from the our eyes, then the size of that object will goes on decreases. Means whichever the object that is nearest to the our eye, that object looks larger. If I place the same object away from the eye, but the size of the object is same, but that object looks very smaller to our eye. Means the distances create the difference in the size of the object that is displayed on the screen of the monitor or that is displayed on the view plane like this. Third case says that, or before going to third case, see the second case only. In the second case, I kept projection reference point at the distance 2 meter from the view plane or from the clipping window. Then definitely object size will looks very smaller. If the object is near, looks larger. If the object is far, it looks smaller like this. These are case 2. Case 3 diagram, you see that. When the projection reference point is very far from the view plane, means if I place the projection reference point at the infinite distance from the view plane, then perspective projection becomes parallel projections. Or perspective projections, in case of perspective projection, our projections lines are converging at the certain point. But when you place projection plane infinite distance from the projection reference point, projection lines will become perspective concept to parallel concept. Means here our perspective projections, in case of perspective projections, our projection lines has to converge at the certain point, that is called converging point. But here there is no concept of converging point, because we kept view plane far away from the projection reference point, so that object will become invisible. Means in case of perspective projection, if you place the object between near plane and far plane, then only object is visible. If you place the object after the distance of far plane, that object will become invisible, and perspective projection will become parallel projection concept. So this is the case 3. So perspective projection derivation is there with respect to first point. So I kept this slide is empty here. So one derivation is there with respect to this topic. I would like to derive the derivation in the next video lecture. So today I discussed one of the most important topic, that is called perspective projection coordinates. So these all are the theory today I discussed. Tomorrow I will going to discuss how we can project a point P on the space into the projection plane, and we are going to determine projection perspective projection coordinates. Now this is one topic today I discussed. Now I would like to discuss next topic, and this topic is very important with respect to whatever the theory till now I covered. The topic name is called OpenGL orthogonal projection functions. Means now it is the time to discuss what are the functions with respect to three-dimensional viewing OpenGL will support. So OpenGL will support two types of functions. One type of function with respect to orthogonal projection or parallel projection, and second type of functions with respect to perspective projections. So whenever we are using projections or whenever we are displaying three-dimensional object on the two-dimensional screen, we need to activate one of the function called GL underscore projection. So here we are using one function called GL matrix mode. This GL matrix mode OpenGL function activates or it defines which type of functions or which type of projections you would like to use in your OpenGL program. Either you can use parallel projection or you can use perspective projections. First you need to execute GL matrix mode and pass the symbolic constant called GL underscore projections or projection, not projections, GL underscore projections. In almost our lab programs, whenever you are displaying 3D objects, in all the programs we are using GL matrix mode. It says that whether you are using perspective projection or parallel projection. So which type of projections you are using, it defines. Next, if you want to use parallel projections, especially orthogonal projections. So when you want to use orthogonal projections in our OpenGL program to display three-dimensional object on a two-dimensional screen, we are using one inbuilt function called GL-ortho. This GL-ortho function defines we are using parallel projections to project given three-dimensional object description on the screen of the monitor. So as we know that when we are using orthogonal projections, our projection lines are always perpendicular to the view plane. So when parallel when we're using parallel projections, we know that projections lines are perpendicular to the view plane. Then you can view either front end of the object or top end of the object or sides of the given object. So this GL ortho function will create one rectangular parallelepiped shaped weaving volume, as we already discussed. What is the shape of the weaving volume with respect to parallel projections? So it create one cube, or I can say that the shape of the cube is like a parallelepiped shape. Now, if you want to create cube, we need to define 6 parameters like x min, y min, z min. But here I am taking z means z near, and I need to define x max, y max, and z max. So z max I am defining d far, distance from the far distance here. So totally 6 parameters I need to pass to create a weaving volume of shape parallelepiped structure. So GL ortho will take x window minimum, x window maximum, y window minimum, y window maximum, z window minimum, z window maximum it is. But I written here distance, near distance and far distance. This is nothing but z-axis value, like positive z-axis and negative z-axis like that, right? This GL ortho function creates the orthogonal projection in our OpenGL program. So it selects the clipping window coordinates and also it defines the distances to the near and far clipping planes from the weaving origin. From the weaving origin. So that is nothing but near means d near, far means d far. For example, even though if you are not passing any argument to the GL ortho, GL ortho will use default orthogonal projection coordinates are -1, -1, -1. Means here, as you can see that this -1 is nothing but x min, this +1 is nothing but x max. First x min, x max. X min is -1, x max is nothing but +1. Similarly, y min -1, z min y min -1, y max +1. But with respect to z axis, I return z min, I return 1, z max I return -1. Means we are weaving that object from positive z axis to negative z axis. Because of this reason, z near, d near is +1, d far is -1. Means if the object is between the distance 1 to -1, or if the object coordinate position with respect to z axis is between 1 to -1, then only object is visible. If object is after d far distance, or if the object coordinate position I defined in my OpenGL program with respect to z axis is after -1, that object is not visible. So this is the default coordinate positions. And whatever the default coordinate positions I defined with respect to GL ortho, I can convert this to GLU ortho 2D also. In case of GLU ortho 2D, we have four values there. We have four values, that is x min, y min, x min, x max, y min, y max, y min, y max. Here d near and d far is not defined, but by default it will take d near and d far is 1 plus 1 to -1. By default I am discussing what I am telling, using GL ortho default orthogonal projection coordinates. It is similar to using GLU ortho 2D with respect to default coordinates of GLU ortho 2D, that is -1 plus 1, -1 plus 1, and d near d far is not there, means z axis is not there here. Even though if z axis is not there, it will take z axis value +1 to -1. This is in case of 2D, this is in case of 3D. Both are same. Both are same. But please you remember, even though it is GL ortho, it is a 3D, while projecting image on the screen, or when you are displaying image on the screen, you are displaying image on the two-dimensional display device only. So GL ortho is almost same as GLU ortho 2D with respect to these coordinates. If you are changing coordinate, then that is a different issue, or that is a different matter. Or I can say that GL ortho is totally different from GLU ortho 2D. So I would like to conclude this slide. By using this slide, I can use GL ortho function, three-dimensional weaving function, to create one weaving volume for the parallel projections or for the orthogonal projections. Next is how to create or how to use perspective projections in our OpenGL. So when you want to use perspective projections in our OpenGL program, we need its function, corresponding functions. So OpenGL supports two types of perspective projection functions. First one is called GL frustum. Second one is called GLU perspective. These are the two types of OpenGL functions we are using to create perspective projections. As we know that when we are using perspective projection, the shape of the weaving volume, see that here, I displayed clearly. The shape of the weaving volume is like a pyramid or like a frustum. Because of this reason, we are using two types of functions here. First one is called GL frustum. So this GL frustum creates one weaving volume of shape like a pyramid. So as you can see that GL frustum, again it will take 6 parameters only. GL ortho will also take 6 parameter. GL frustum is also take 6 parameter. The reason of taking 6 parameter is we want to create cube. Please you try to understand. We want to create a cube of different shape or different structure. Now GL frustum will take same 6 parameters. Same 6 parameters. But this function has the same parameters as orthogonal projection function, but it creates perspective projections in our OpenGL program. And I highlighted here d near and d far. These parameters specifies distance from the coordinate origin to the near clipping plane and coordinate origin to the far clipping plane. So this is the distance between the projection reference point to the near clipping plane and projection reference point to the far clipping plane. So this is this slide. I would like to conclude this slide. So in this slide, if I want to create perspective projection viewing volume, then I should use GL frustum. GL frustum creates the perspective projections in our OpenGL program, and it project three-dimensional object on the view plane using perspective projections. And one more function we are using, that is called GLU perspective. This GLU perspective is one more type of function we are using to create perspective projections, to translate the object position from the three-dimensional space to the view plane or to the monitor or on the screen of the monitor. Then the syntax of GLU perspective is like this. It will take theta value, aspect ratio of the clipping window, and the distance between projection reference point to the view plane, that is d near and d far, or you can write z near and z far. These are the four parameters GLU perspective will take. But in this syntax, we know that aspect ratio is nothing but it is the ratio of width to height of the clipping window. As you can see this example, see the image, second image. This is the width of the clipping plane and this is the height of the clipping plane. So aspect ratio is nothing but it is the ratio of the width width to height of the clipping plane. And we know that what is d near and d far. D near is distance between projection reference point to the view plane. D far is distance between projection reference to the far clipping plane. Far clipping plane. Now we know all these three parameters, but this is the first time we are using theta. So Theta is nothing but it defines the angle of view. So as we discussed in the previous slide, field of view or angle of view, that is nothing but theta value. So I written clearly, it is the angle between the bottom to top of the clipping plane. Bottom to top of the clipping planes. Generally, when I want to capture any image by using real camera, the theta value is 180 degree. So I given one real life examples in the previous video lecture. If I would like to take one group photo, then by using real camera, if I want to take one snap called group photo, one of the object in that group photo I will select as a fixed point, and I will adjust my lens in a such a way that the angle of view is 180 degree. If angle of view is 180 degree, then only you can capture that entire object. Same concept we are using in synthetic camera by defining concept called theta. So now theta is an angle between bottom to top clipping planes of the pyramid or of the our frustum like this. Now these are the parameters we are using, and here I specified clearly d near d far it is a distance from the coordinate origin, means from the camera origin to the near plane as well as far clipping plane along the negative z view, along the negative z view. So here you can see that here this is nothing but our real camera, and this is nothing but our synthetic camera. Real camera and synthetic camera. And when we are using real camera, look vector is there. This look vector is nothing but viewing direction. We are viewing this object in this direction. This is called z-axis value or looking viewing direction. When you are viewing in this direction, this will become z-axis, and opposite to z-axis is nothing but view up vector. This is nothing but y-axis value. This is nothing but y-axis value. Now I would like to conclude this slide. In this slide, we learned how we can use GLU perspective function to create perspective projections to translate position description of the object on the projection plane. Now as you can see that I said field of view or angle of view. So this is the best example here, right? So generally we will tell focal length in the real life or in the real camera. We will tell focal length here. See that here. See this, please. You see that here. Camera position is here. That is called projection reference point. And here this is nothing but angle of view, right? Angle of view. So wide angle lens corresponds to the larger angle of view, right? So here you can see that if your real camera of focal length is 28 mm, you will get the larger size image. If it is a 30 mm, means you are reducing the angle of view. If you are reducing the angle of view, the size of the object is also goes on decreases. Here our focal length in real camera 28 mm, 30 mm, here 80 mm. This means these are the focal length with respect to real camera. Same focal length we will use angle of view in case of synthetic camera, that is called theta value here, theta value, right? So last function in case of three-dimensional viewing is GLU look cut. So this is also one more type of three-dimensional viewing function. So we need to use look cut, GLU look cut. This is also one of the viewing function. You can see that how GLU look cut will work. So GLU look cut function will take 9 parameters here, and the 9 parameters are classified into three things. three things, right? First, GLU lookup will take P naught value, P reference, and VWAP vector. So whenever we want to capture any image using real camera, we need to define three things. First, you need to define position of the camera. That is nothing but P naught. When you define position of the camera, it is nothing but you selected origin of the camera. So origin of the camera, we are selecting X naught, Y naught, Z naught. After selecting origin of the camera, you need to define reference position. Means when you want to capture any image, in that particular object, one of the pixel position, you need to consider it as a reference point. So you can say that P reference having three coordinates, X reference, Y reference, Z reference. So this is the second parameter we need to consider. After that, you need to define VWAP vector. So VWAP vector is nothing but y-axis value. See the camera position here. This is called viewing direction. Viewing direction means that is called, we selected P reference here, P naught also here, and this y up vector is nothing but y-axis value with respect to our real camera. Or you can see the synthetic camera. Position of the synthetic camera is at the place called location. When I kept the camera here, I am viewing in this direction. This is look at direction or viewing direction. When you are viewing in this direction, I can say that we are viewing the object towards the negative z axis. This is nothing but our look at point here. Look at point. Look at point. Now, here we need to decide three things. Our origin of the camera is nothing but P naught, and our reference point is nothing but, this is nothing but our P reference point, and our lookup vector is, this is the lookup vector. This is nothing but y-axis value. So this is real camera and this is synthetic camera. By default, OpenGL viewing function called GLU lookup will take the following parameters. Means the origin of the camera is 0, 0, 0. That is a P naught value. And our P reference point is, we selected one of the reference point when we want to capture the image, that is x-axis value 0, y-axis value 0, and the z-axis value we return -1. So this -1 is nothing but, I can say that this is nothing but z for value or d for value, means this is nothing but our P reference point, and its coordinate position is 0, 0, -1, 0, 0, -1, and our camera is located at the center of this plane, that is x is 0, y is 0, z is 0. Now V reference point is, see that here, V reference point is, our camera is parallel to the y-axis. When camera is parallel to the y-axis, then x is 0, z is 0. X is 0, z is 0, only y-axis value is 1. So this is nothing but our VWAP vector. So if you want to execute GLU lookup, you write GLU lookup 0, 0, 0, P reference value 0, 0, -1, VWAP vector value, 0, 1, 0. So GLU lookup will take 9 parameters and it projects three-dimensional object on the space onto the two-dimensional display device. So these are the four types of three-dimensional viewing functions we are using in OpenGL to project three-dimensional object on the two-dimensional screen of the monitor. So today we discussed different concepts like perspective projection, coordinates. This is the one concept I explained, but derivation is pending. Next, I explained second concept, that is called OpenGL orthogonal projection functions. So we have four types of OpenGL orthogonal projection functions. First one, GL ortho. It defines parallel projections in our OpenGL program. This is the first type of OpenGL function. GL frustum. This is the second type of OpenGL function, or second type of three-dimensional OpenGL function. It creates perspective projections. Third type is called GLU perspective. It is also similar to GL frustum. It creates three-dimensional perspective projections. Fourth type is called GLU perspective. This is also one of the three-dimensional viewing functions to display or to project three-dimensional object on the screen of the monitor, or we need to project the position of the object on the projection planes. Thank you.